just wanted to mention I've got a really raspy sore throat today. Okay, so it's our last day. There's a ton of other stuff I would love to talk about. I'm hoping that, you know, if you haven't printed out some of the notes, that you'll go ahead and print them out, put them together in a binder or whatever. I don't know how long they're going to stay online or whatever, but I think that I hope they're a useful resource. I've found, even when especially when I started teaching as a new professor, that I would go back through my class notes and read them and realize that I didn't understand them at the time so well, and that I was able to learn much more than later on. So, you know, it is overwhelming. You're learning a ton of stuff, and you're learning it fast, and some of it you do a homework assignment for, the rest of it blows by. The point is that, you know, whenever you need it in the future, you can go back and learn it for real, okay? So, and that's in practice really how it works, I'll be honest with you. Okay. So last time we left our superhero off, we talked about pressure broadening, and we basically focused on this sheet here, which said n equals 2, n equals 3, 4, and 6 for the different indices, and we said that pressure broadening gives you a Lorentzian broadening profile. We showed what a pressure broadening profile looks like here, where you have the narrow Gaussian core, and then you have the damping wings off to the side from the Lorentzian. These notes then describe what are the important regimes for each of these types of broadening, and then here's an example of an H-gamma line that is going from a giant star to a main sequence star, I believe, or I can't remember exactly. Yeah, a B3 star, showing the broadening. And then here is a relationship between temperature and I believe it's the equivalent width, showing how the sum of pressure and thermal broadening behave on this diagram. Okay, pressure broadening is also known as collisional broadening, and so the next 1, 2, 3, 4, 5 pages of notes discuss them in detail, okay? But if you get to the 7th page here, I just want to let you know, remember I told you that the Lorentzian of pressure broadening, you know, basically some constants, and you had gamma n over 4 pi times lambda minus lambda transition squared plus gamma squared over 4 pi. I can't remember how that goes. Is that squared? It's been a long time since I wrote down a Lorentzian. Yeah. So basically, you have the natural broadening Lorentzian that we talked about, which depends upon the damping constant and the oscillator strength and whatnot. And then you have the pressure one, and there's some constants out here, which again, this is usually written in it with pi e squared over MEC type of thing. And then it has the natural width here, which is a function of which type of broadening you're talking about. If you're talking about an H-gamma line, then you're probably talking about linear Stark broadening, which is hydrogen being broadened by impulse collisions with protons and electrons in the gas. And so you can derive this gamma So basically, I kind of am going through deriving that gamma, which you won't find in textbooks. I had to like kind of come up with this stuff myself. But in the end, there's a derivation in this box, gamma sub n equals 2 pi p sub c, which that's the partial pressure of the perturber. The temperature raised to some complex index, which is a function of n. N equals 2 linear Stark, n equals 3, what was it? N equals 4 quadratic Stark. I'm sorry, I'm kind of sick and I'm not thinking very clearly today. 6 was van der Waals, 3, anybody? Resonance, I think it was resonance. Okay. So anyway, the n goes in there, and then there are these physical parameters which are basically integrals that have to do with the atomic structure for the different atoms. And then you have the center of mass, behavior between the perturber and the absorber, and then you have another index to the end. So the point is, you can come up with a good approximate formula for what the gamma n is, and notice that it depends upon the pressure, depends upon the temperature, and then some other constants that are, regular physical constants. The point is there's some gas physics in there. So if you're going to make a synthetic profile and you're going to include pressure broadening in it, you're going to want to convolve your Lorentzian for the natural broadening with the Gaussian of the thermal and turbulent with the Lorentzian of this. And again, your thermal broadening function was a function of temperature. Turns out your damping constant of your... Yeah.
The strip. Is the strip on?
Thank you. Yes, so I don't run out of battery halfway through. Good catch. Thank you. The point is you've got some gas physics in there, so now your model, your tau, has a pressure of the perturber and it has a temperature in it as well. And so again, those are free parameters. You tweak your temperature, you get out a profile, you plot it to your data, you look and see if it matches your data. So anyway, that's just to show you, and this basically down here, these boxes are basically giving you the temperature dependence for the different n. N equals 2, 3, 4, and 6 here, what the power is for the temperature, just so you can see how it depends upon temperature. Right. So, okay. So someday, if you want to go back and learn all that, if you're actually going to be worried about pressure broadening lines, you can use that as a resource, so you can go in the textbooks and try that. Here is an example of Mahalis's write-up. As you can see, it's terse and it's highly technical. All right. So I've taken what I thought were the essentials from various textbooks and put it together in this elongated 7 pages of notes. So you can get an idea of what it's like. All right. So that is it for pressure broadening that I would like to talk about. Again, I never use it because I'm always in the ISM or the intergalactic medium and not stellar atmospheres. Stellar atmospheres, density's high, pressure broadening is important. So basically, this is a summarization of getting the total cross-section. Okay, if you remember, tau lambda was the column density of that absorber times alpha lambda, where alpha lambda was the convolution of this natural convolution with the pressure broadening, and those were Lorentzians, and then you convolve that with the 2 Gaussians. If you will, it's a redistribution function. Actually, it's not really a cross-section, but it's expressed as a cross-section of thermal, and then you convolve that with the Gaussian, which was turbulent. Okay, So these were the two Lorentzians, and these were the two Gaussians. And you ended up with a profile that was a Voigt profile. Okay?
You said yes, or the other day, that you want to do like the Lorentzians, convolve those, and then convolve the Gaussians, and then convolve those two together, or is the order important, or?
Actually, it's interesting. You don't really have to do the convolution on the computer, because there's an expression for the Voigt function, and this sigma natural is a function of lambda, rest, oscillator strength, and damping constant. And sigma pressure was a function of, I think it was pressure and temperature, and for a given n, right? And then, so these were the two Lorentzians, and then the sigma for thermal was a function of T and the mass of the ion, I believe. Well, those masses of ion. So I think it's basically temperature, and then sigma of turbulent was of V turb. And so basically what's nice about the Voigt function is that you can take these parameters and this gamma n really is a function of these two things. So actually I should probably say this is a function of gamma n, okay, where gamma n is of P and T, okay. So the point is that you get a new Lorentzian here where the damping constant, I guess I'll call it bar squared, is right. So this all you're saying is you're not actually doing the convolution on the computer. You're using the same property here, that the width of the Lorentzian natural and the width of the pressure are just added in quadrature to give you the new width of this Lorentzian, which is the convolution of these two. You see what I'm getting at? Mm-hmm. And the same thing happens here. You have this Gaussian, and sigma squared is equal to basically, I'll call it B if you want, B thermal squared plus B turbulent squared, okay? Where B turbulent is just V turb, and B thermal is just the square root of KT over M ion. And so basically now you've got a Voigt function, which is a function of these two things, and it makes it much more simple. And if you want to know what that Voigt function looks like, I'll show it to you in a second down here. Right, so basically these notes are going through those four and then showing you the expressions for them again, just to summarize, okay? And this is the thermal and the turbulent. And so you get what's in this box here is the final expression for alpha. So alpha, this right here, okay, is equal to pi e squared over mec squared lambda rest squared times the oscillator strength times the Voigt function, okay? And the constant, this function here, is an integral, it turns out. There's this extra constant here, square root of pi times delta lambda d. Do you remember what delta lambda d was? It's basically this width, but in wavelength, okay, instead of velocity, times this thing called a Hertzian function, which people have lookup tables for, but if you want to do numerical integration on your computer, you can. It's basically this integral here. So t is your dummy variable for integration, effectively wavelength. And then a is lambda minus lambda r over delta lambda d. So this is basically your alpha of lambda at some wavelength. This is a rest wavelength. This is function of a and b, okay, which is normalized by the Doppler width, and then is this integral at a and b. A is basically a of lambda. So at that lambda, you evaluate a and you plug it in. So basically this a is the lambda variable, okay? And then b is the normalized also by the Doppler width, and it's just equal to gamma lambda r squared over 4 pi c. And actually, if you don't mind, what I'm going to do is I'm going to write this as gamma bar. In other words, this gamma is the gamma that you get in quadrature from the natural and the pressure broadening. My applications, this is just gamma natural. Okay. So the point is that this is basically a constant for that transition because, well, it's a constant for the transition if it's only the natural broadening, because it only depends upon this, it's just this number here based upon the Einstein A coefficients. If it's the full gamma with pressure broadening, then it also depends upon some of the gas physics. Okay. So anyway, it's a constant for the integral, and then the integral is done at each a, which is to say at each lambda, and then you get out the value at that lambda, you plug it in, and you got alpha at that lambda, you multiply it by your column density to get your tau, e to the minus tau, you got your model for your absorption line. So you wanted to be a scientist, huh?
Not really, I'm just kind of
Great answer. Not really. I'm just watching. Entertainment value.
yeah.
Okay.
And F is the
Where's that?
in the cross section.
Oh, this is the oscillator strength.
That's a cross section.
Yeah. It turns out that the natural Lorentzian actually provides most of the physical constants that are out front. So this is borrowed from the natural Lorentzian, and then these things are basically the convolution of the Gaussians and the Lorentzians together as a function of wavelength, and here's the width of the Lorentzian. All right. So the delta lambda d contains the thermal broadening information. So the delta lambda d is basically the information from the Gaussians that comes from the quadrature sum of the turbulent plus thermal velocity, and then this b has the gamma from the Lorentzians. So this is basically, b has information of the Lorentzian width in units of the Doppler width, and a is where you are in wavelength in units of the Doppler width. So that's where this is the Gaussians, this is the Lorentzians, and you get this integral at each wavelength.
Just that easy.
That's why we have computers today. Imagine the good old days when you had to run this stuff by hand. I can see all the excitement. All right. So basically what you do is you model things this way, and you tweak your temperature, you tweak your number density from your model, and get out the new gamma, and I get out a new delta lambda D, and you try to see if your profile matches. And then you got one transition from one ion. And you got to do it for all your absorption lines to get out all your individual column densities. And they all have to be consistent with your gas model. Good luck with that. Okay. Fortunately, in my business, we get something like 4 or 5 transitions, and that's all we have to work with. You know, carbon 4, carbon 2, silicon 2, silicon 4, magnesium 2, oxygen 6, hydrogen 1, and off we go. And we don't worry about, we put the rest of the metals in our gas, but we don't have to worry about what they're doing really. Okay, moving on to rotational broadening, which is one more term in this baby. Now you appreciate that doing stellar spectroscopy is not such a piece of cake, is it?
Appreciate the strong way of putting it.
Appreciate this. Have an awareness. So, okay, but what I'm hoping is at least you're getting the background, the broad brush picture here enough that, in principle, if you had to go back and do it, you have a good starting point. That's the point of classes. I'm feeling good that we're covering that ground. I don't know if I'm doing a good job of it, but okay, so rotational broadening. This is a diagram, 4 diagrams, which are basically showing spectral type and then rotation speed. And this is the rotation rates of dwarfs, and you can see somewhere here around dwarfs, meaning main sequence stars, that stars hotter than F5 have a wide range of rotation speeds. But if you get to lower temperature main sequence stars, they have much smaller. So you don't usually have to worry about rotation broadening on the cooler stars if you're a main sequence. Now, the cutoff of this changes with luminosity class. If you go to the diagram to the right, you see that it's somewhere around a G0 for the subgiants that you see this transition. If you go to the giant 3 stars, it's around a G2, and I believe this is rotation of close binaries, showing that if you're in a binary, all bets are off, that crazy things can happen. Okay. So, given that rotation up to the levels of 300, 150 kilometers per second can happen. Now, thermal spreads, we talked about the B parameters. A thermal spread, a temperature of 10,000 degrees for hydrogen causes a thermal spread of about 30 kilometers per second. And 10,000 degrees causes a thermal spread of about 5 kilometers per second for, let's say, an iron line. Okay? Those are small potatoes compared to rotation speeds of 150 kilometers per second. Okay? So you'll have a thermal component here, or a turbulent component. But if you've got a fast rotator out here that's doing 150, 200 kilometers per second, that is going to broaden your line over a much larger wavelength than what the thermal broadening is going to do. So one thing that you should know in science is, okay, let's add the fact that we're going to convolve now with some kind of, I'm going to call it G of delta lambda, because that's what people call it. If this is a broad profile over 150 kilometers per second, it is going to perhaps dominate. It's certainly going to dominate the Gaussian, which will be in the core. Depending upon how intense the pressure is or how high the column density is, you still have to consider the Lorentzian, because the Lorentzian, when the column density goes high, those wings those far out wings in those lines, because you saw those profiles that go like that, right, actually become important. So if you've got a fast rotator, you might be able to ignore the thermal component and the turbulent component, because it's only going to deal really with the core of the line. Okay. So I'm not going to go through the derivation in detail, but it's here for you. One of the other things to think about is limb darkening. Okay, we'll come back to this in a minute. Let's skip it for right now. Okay, but here's how you do the derivation of rotational broadening. Okay, you basically have a rotating star, a vertical sliver with some width dp has a constant velocity on all locations, and if it's rotating symmetrically on the negative side of the star coming toward you, it's the same thing. You have that strip, all the velocities on that strip are the same, all the velocities on that strip are the same, and then it's just a question of integrating over all those strips with different velocities. Okay, so here's some derivation of how you do that, and then here is how you account for the inclination of the star. Like I said, it's a pretty simple derivation, like you would see in an undergraduate book, so you can go through it yourself if you want. But in the end, you get some simple formula down here that looks like this in terms of delta lambda. Okay? So in the end, this I of lambda d delta lambda is this function right here on the right hand side. If you plug in and normalize it to unity, you get the constant a out in front. That's given right here. So if you write it out in its full glory, including sine I, if you have a constant rotational velocity v sub r, that's a free parameter. If you don't know the rotation of your, again, now you're adding another free parameter to your model. You might not know the rotation speed of the star, v sub r, and sine I, you might not know the inclination. Then you get this particular equation as a function of wavelength here. That's in the box. Okay. Now, it turns out that you can account for the fact that this derivation and that formula assumes that the entire disk is single luminosity or single flux, surface flux coming off of it. But in fact, you've probably all heard of limb darkening before. Okay. Because of the optical depth effect, when you look straight into the disk, the observer's over here looking at the star. At the disk, you're looking to deeper layers, so you're seeing hotter material for some fixed optical depth. You're seeing a deeper physical depth. When you look at the limb here, okay, that same optical depth means that you're looking at a higher physical depth in the star, and as you go out, the temperature is lower, so the flux coming from that layer, I shouldn't say the flux is always conserved, but the intensity coming from that layer is lower. And so as you go from the center of the disk to the limb, you see that in fact the intensity will tail off. And in fact you see a profile that looks like this relative to the center of the limb in terms of the intensity. So that means instead of assuming the face of the star is constant brightness everywhere, okay, you have to account for the fact that up here you have less brightness than you do here. You see there's a brightness variation along that strip. Okay, less brightness to the max brightness to the minimum brightness as you go down. So if you include that into your derivation, yak, 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 okay, it's a kind of an ugly derivation, blah, blah, blah. It's on this page here, rotational broadening versus limb darkening. You get out a nice formula at the top of the next page. So if you want to include limb darkening, your A and your B are basically the two constants of linearity. I forgot to mention those. My bad. Let's go back to the limb darkening plot. Okay, notice that the limb darkening as a function of this cosine theta, okay, theta going this way on this angle, you're familiar with theta, is a linear, almost like a linear function. So people approximate it as a linear function, a plus b cosine theta here. So your a and your b are basically, you choose those based upon what star you're looking at. People have cataloged these. You could say, oh, it's an F50 star, a is this, b is that. It's in, you know, in the old days it used to be in Allen's astrophysical quantities. You could look that up. Now you just go to the internet. Okay. So anyway, you get this formula here, which is a function of a and b. Okay, very good. So now you know what the functional form of this is. So all of these together are this, but then you have to convolve this with that formula that I have here. Okay. Guess what, folks? There is no simple Voigt profile analogy formula. This, you have to do this brute force. You have to convolve it in the computer. All right. So in the case of rotational broadening, the good happy days of having a nice closed form formula are over. You have to actually do the convolution. What does this function look like? Here's the diagram down here. Okay. So you can see what the total looks like, and then for the two terms in the formula that includes the limb darkening, which is more realistic, you can see the two terms contributing and what the total shape is. And in this case, you can see that that is a very odd looking profile. So if we go to the next page, let's take a look at a spectrum of a luminosity class 3 G1 star, and if it's a slow rotator, you'll get these profiles that basically are the convolution of these four terms. It looks to me like the pressure term is not terrific in any of these particular lines that are being shown, because usually the pressure term dominates in the hydrogen. But if you have the rotation, you can see that the absorption lines just look incredibly funky because they're blurred out by this rotation function, which is dominating the line shape. Right? So if you ever look at a spectrum and you see weird looking lines like that, you now know you're seeing lines that are dominated by a fast rotating star. Fair enough? All right. Okay. Pause. Any questions? Okay. So let's just write up now what we have here. We have G lambda, and this is a function of B rotation and sine I. So the number of free parameters are really piling up. Pressure, temperature, turbulent velocity, V rotation, sine I. You have to, now you've got sort of a multi 8 parameter, 5 parameter problem, because you want to try and determine it all simultaneously by measuring, you know, how many points do you have along a rotation curve. Right? Okay. Now I have to tell you about one more thing, which is really a pain in the pick your favorite body part. Okay. So that, everything we've talked about is your model to get tau. That's just to get the optical depth. Okay. line profile, looks something like that. So once you get tau, your model is given by that. Okay? You're like, so that's a piece of cake. Getting tau is hard. Now I just multiply it by some flux coming off the star or continuum or whatever. Or either that, or I just take e to the minus tau and I plot up my model and compare it chi-square. Right. One of the things that we have not talked about in this class, my understanding is that John is supposed to talk about this, or the semi-unspoken agreement was that I was going to lay off talking about spectrographs because he talks about spectrographs. Okay, so you've learned about spectrographs a little bit, something or two. An observation. Okay, so second years, but not first years. Okay, so that shouldn't make too much difference because I'm just going to tell you the final result of something. Okay, I'm not going to go through some of the basics of what happens. But let's just put it this way. You have light. Okay, here's the atmosphere of space, and here's what your profile looks like coming into the atmosphere of space. Okay? And it comes through the atmosphere to your telescope. And in fact, by the time it gets to the top of the telescope, it's changed a little bit because of turbulence and things like that in the atmosphere. But most of the violence to the shape of that profile happens here. Okay. The one that matters the most is after it goes through the slit of the spectrograph. Okay. The first thing it does is it hits a mirror that collimates it. The beam gets collimated and hits a dispersing element, either a prism or a grating. Okay. And then that separates parallel beams of different colors, which are then focused down onto a CCD at different physical locations. All right. So that process of going through the grating and focusing it down is not perfect. And so some wavelengths get blurred together a little bit. And there's something that's called the instrumental spread function. Okay? So basically, let's consider a perfect absorption line coming down from space that's truly a delta function. All right? It comes through the telescope and it comes out and it looks something like this. It's been spread out. Okay?
Is it just because you probably got this? Is it just a result of resolution limited? Being resolution limited, or is it actually something that physically happens in the instrument?
It physically happens. The light actually is not spread out, dispersed in perfect monochromatic way. Whenever you disperse light out, you disperse it in a small distribution. So you might have the light come in, and red light goes out at 45 degree angles from the disperser, and blue light might go out at 30 degrees. But a given wavelength of red, 65, 63, for example, doesn't go out exactly at 35 degrees, whatever. There's a distribution function, a small distribution function, where the peak is at 35 degrees, and then smaller, less intensities at 32 degrees, 31 degrees, and stuff like that. And so by the time you focus that back down in the CCD, you've ended up blurring the light out a little bit. Okay? Now, so this is called the instrumental spread function. And if you threw a true delta function through the telescope and the instrument and get out, usually these are almost perfect Gaussians. They're not always Gaussians, but they can be. And so that you basically have this functional form here that is the instrumental spread function, which is basically telling you how the light's blurred out when it gets redirected in direction, okay, at a fixed wavelength. All right. So what I'm showing in this diagram here, I generated these. Here's some absorption profiles as they come in from into the telescope, into the instrument. And you can see that they're spread over a delta lambda of minus 0.6 to 0.6, with one line here centered at 0 in delta lambda and one centered here at 3. All right. So we're going to look at different instrumental spread functions, which are given by these Gaussians here. We're going to assume a nice Gaussian, okay, which is basically telling you how much a fixed delta function of wavelength, monochromatic wavelength, will get spread out, first in angular space and then in wavelength space on the detector. Right. Now, we define the resolution of an instrument using a constant called R, and this is actually a constant of the instrument. So if you're at 65, 63 and your resolution is, say, 1, well, let me see if we can do this. Delta lambda equals lambda over R. Okay. So let's say you're looking at 1 micron, 10,000 angstroms, and your resolution is 10, okay? So that's 1,000 angstroms. That means that the width, that wavelength is spread out over as 1,000 angstroms. That's crappy resolution, right? Let's say you're looking at 5,000 angstroms and your resolution is 5,000, then your instrumental spread function takes a single wavelength at 5,000 angstroms and spreads it out 1 angstrom. At 10,000 angstroms, if your resolution is 5,000, it'll be spread over 2 angstroms. So the resolution is constant, but the spreading of the light goes linear with wavelength. Okay. So this R factor, this delta lambda here, is related to the full width half max of the Gaussian, okay? And that full width half max related, you're used to a Gaussian in terms of sigma. I believe that there's a factor of 2.35. So if the instrumental spread function is a Gaussian with some sigma, okay, if that's the instrumental spread function and it has some sigma for the Gaussian, 2.35 gives you delta full width half maximum, and that's the delta lambda that goes here. Okay, and so then if this turns out to be 5, if this well, that's the delta, and this delta lambda changes as you go to longer wavelength. It gets broader and broader and broader, and it goes linearly. Okay, this is a constant for the instrument. This actually grows, and it grows with lambda, as you can see. Okay. All right. So in the blue, this delta lambda will be narrower. In the red, it gets broader and broader, but the factor R is always the same. Now, so what I've done now is I've convolved for different R factors, 20,000, 9,000, 4,500, 2,250, and 450. I've convolved those. So here is high resolution, 20,000. Delta lambda is going to be very small, 0.06 for this rest wavelength. And as you can see, the profile that you measure, looks a lot like the original profile that came in. So the higher the resolution, the smaller the delta lambda, the less the blurring, the more your profile is preserved, higher resolution. As you go to lower resolution, let's drop down to R of 9,000, you can see now that the two profiles have become blurred and blended. As you go to R of 2250, where you're very much broad, now look at the difference here. This profile is very narrow, between minus 0.2 and 0.4 delta lambda, but the R of 2250 has a sigma that's almost plus or minus 0.5. So it's much broader on this. You see what I'm saying? The width of this is broader, is almost the full width of this plot right here. And so you can see it blurs it out entirely. Okay. So as your resolution goes down, the depth of your line goes down and the width of your line goes up. And if you want to actually resolve the shape of your line, you start to lose it altogether. All right. So if this is the profile coming in through the front end of the telescope, then you have to take it so that your actual profile you measure, okay, is this instrumental spread function convolved with the profile that came in. So here's the profile that comes in from space into the front end of the telescope. You convolve it with the instrumental spread function, all right, and you get out I measured. And so that's what that plot is showing you that I've done. Okay. That's the profile that comes in. Here on the left is this. Then this is the profile here that I convolve with it, and I get out the profile on the right. All right. So as you can see, if you want to become a professional spectroscopist, you're going to have to know how to convolve if you want to model your lines yourself. And be honest with you, convolution is done best with Fourier transforms. And there's all kinds of numerical ways to feed these functions into fast Fourier transform subroutines, and boom, out comes your convolved profile. And then you can do something like what I've written down here at the bottom, which is to do a chi-square fitting of your profile from your model. So, ladies and gentlemen, not only do you need, if you want to do this work, to know how to model gas physics, well, that's later. Let's just say we want to get one absorption line, just one absorption line. We need to at least consider which physics is going to be important. Thermal, going to be important, or rotation, going to be important. Natural, always got to have natural. That's the atom itself. Okay. Always got to have this. This only, probably, mostly main sequence stars. Okay, dwarf stars. IGM, no. ISM, no. Okay. Thermal, almost always. Okay, because gas is hot. That causes the atoms to spin. Turbulent, well, you know, in this case we assumed a Gaussian turbulent velocity. You might have a complex wind where you have to actually model this as some kind of flow, which is not Gaussian, and then you have to convolve that, so your Gaussian convolution bets are off. But for me, I just usually have some small turbulent velocity, always have a thermal component, always have natural. If you're doing stars, you want pressure, and if you have rotation, you have to have this. So, you know, you've got these free parameters, you got these calculations for these formulas to make these, you convolve them all together, okay? You get out alpha, you guess at some column density, you get out your tau as a function of each wavelength. Now, remember that you had to perform that integral for the Hertzian function to get the Voigt profile at each wavelength. You have to do an integral at each wavelength, each different A, to get out this functional form. You multiply it by n, you get out that functional form. Okay? And then you convolve with the instrumental spread function, which means you got to look up or know the instrument the data were taken with, and you have to figure out what R was, and whether you can actually use a Gaussian, because some instruments are more complicated, like the cosmic origin spectrograph on the HST is not a Gaussian. It's some beast that is actually more complex, and people have modeled it with parameters, and it's a function of wavelength, and you have to convolve that to get out finally some profile that you're going to compare to your data. And maybe do a chi-square fit and go, I think I can do better. Go back here. Well, maybe if I change the turbulent velocity up 10% and the temperature down, or I, yak, and then I recompute it, and I do all the convolutions, and I generate another model, and I do a chi-square ABD. Welcome to the world of fitting an absorption line. An absorption line. Okay. So now you got out some basic constraints, maybe on the temperature of the gas and the turbulence of the gas. Okay. And therefore, and you've got some constraint on the number density through you've got this. When you model things, you want that. So you got temperature, you want that if you want to model it, because you want the number densities of all the ions to get metallicities and things like that. So you might have 7 or 8 absorption lines, some from calcium, some from iron, some from hydrogen, some from who knows what, magnesium, and you need to model all of them like this. You want them all to be probably at the same temperature and the same turbulence, so you have to fit them all simultaneously to get the best value, single value of turbulence and single value of temperature and whatnot, and you have to account for the column density being for the different ions for each of the different profiles, if this is hydrogen or whether this is calcium. And you see what I'm getting at, it gets complicated. And then armed with that information, T and column densities, then you can say, all right, now I'm going to go model my gas, and I'm going to calculate from it what my column densities would be. And I at least have a temperature. Before, when we calculate the ionization balance, we calculate as a function of temperature, but hopefully from your data you'll actually get the temperature. What you really are figuring out now is what are the abundances and what is the depth of the cloud and things like that. So now, in principle, I could hand you guys 7 absorption lines from different metals and ionization stages and excitation stages, and you could first of all learn how to model a single one of those profiles, and then you would apply that model individually to the other 7, but what you eventually want to do is tie all 7 together so that you get a single temperature describing all of them and a single turbulent velocity describing all of them, or a single rotation speed that fits all of them. And then the next thing would be, okay, now I'm going to model my gas, see if I can get out a metallicity or something like that. And that's how you do the physics of gas. It's complex business. Fortunately, people like Chris Sneeden at Texas has written a code called Moog, and you feed it your data, and it goes off and does it all. So there are people who have mastered it, and they've made their work public. And if you look under the hood, you'll find out that it has assumptions, and there are imperfections, as with anything. So people do different things to make their mark in the field and their niche. Chris Moog has become an expert at how to model spectral lines, get out log G, get out metallicities and abundances, the whole 9 yards from the data, rotation speeds. All right. Okay. So, you super excited bunch of people. What we're not going to end up talking about, so I just want to spend the next few minutes telling you what I'm not going to tell you about. Okay, and that is basically the overall, I'm sorry if we had another week, I couldn't really do it justice, but the overall shape of the spectrum. Okay, if you go back to the beginning of the class where you look at the shapes of the different spectra of different temperatures, or if you remember this stuff way back when, you see that the hot stars, really it looks like it has the curve of a black body. And you get to the cooler stars and the peak flattens out. You also have this break, the Balmer break showing up, and it's strongest in the A stars, and then it gets weak again. But actually, what's happening is that the opacity is taking more light out of this area just bluer to the break. That's why the break's getting weaker, not because the neutral hydrogens are changing. Well, they are changing, as you know, but it turns out that there is a broad opacity, a continuum opacity that's dominating this. And I'll just give it to you in short. The reason why the hot stars look black body is because the dominant form of scattering of photons in the atmospheres is electron scattering. They're hot. There's lots of free electrons because the gas is highly ionized. With lots of free electrons zooming around in the gas, photons are colliding into free electrons. They're being scattered around, and that scattering is mostly, to the 99th percentile, wavelength independent. In other words, no matter whether you're blue light or red light, you get scattered the same. Therefore, that opacity is truly gray. Since the light coming in is a black body and it gets scattered around equally at all wavelengths, you still get a black body out. Okay. When you get cooler, your electron density becomes less important and your hydrogen absorption dominates, particularly the ionization break. Okay. But then if you remember right, we talked about at the beginning of the class, as you get cooler, your hydrogen can actually bond with another electron and you'll get something called the H- ion. Okay? And when that happens, the H- ion, I want to show you here in this plot, is a very broad opacity that sort of has the shape of a bell curve across the optical part of the spectrum. It looks something like this. So this is the cross section, okay? And you can see that it peaks here around 6,000 degrees, 7,000 degrees, and it comes down, and then it goes down in the infrared. Remember, the light absorption is the greatest here, right? Because this is the cross section. It goes in. You multiply it by the number density of the H- ions, and it gives you the opacity. And this is where the greatest absorption happens. Is around here, 5,000 to 1,000 angstroms. This is where the Balmer break is. So what's happening is, as you get cooler, is you're absorbing more light out here, redward of the Balmer break. And that causes a flattening. So here's your Balmer break. Now you're mostly removing these photons in the continuum, so the break is smaller. Everybody follow that? So I can show you that, and then we'll be done. Here are and you have them in your notes, I'll show them to you. Here are some main sequence stars showing you the opacities. K star, G star, F star, okay, and you can see here this component here is the H minus ion, and this here is the ionized, or that's actually free, never mind, which I'm not talking about. But here, when you include the breaks, okay, B star, A star, F star, G star, K star, this is due to the ionization breaks, Balmer break, Passion break, etc., in a super hot star from the hydrogen. But if you then, and this blue line here is the bound free from the H minus ion. See, it doesn't even start to become an important opacity at A stars, but at F stars it becomes an important opacity. And so your Balmer break, this gets smaller, but you're also suppressing more photons redward of it, and you end up sort of equalizing out what's going on. So I'm going pretty fast here, but what I'm saying is the H minus ion is what really dominates the shape of the spectrum, okay? And then, last but not least, I'll show you the electron scattering term dominating, particularly in the giant stars. All right. So now I include, here's the giant type 1 stars going up to the B stars. This black line here at the bottom is due to electron scattering. As you can see, it doesn't contribute to the opacities at all until you start getting here to a B star. You start to see it a little bit more discernible. But now, you look at the O stars. You can see now it's becoming competitive with the other opacities. Okay? And so because of that, you can see these opacities are relatively flat, the black line being in the O stars, and so that ends up meaning that you're not modifying the spectral shape of the black body very much because the opacity is fairly flat. All right. Now, I would have loved to have had a whole lecture on that. I apologize.
Jason talks about that in his class.
He does talk about that?
He does opacity stuff.
He talks about continuum opacities?
Those plots look kind of familiar.
Fantastic. I'm going to have a sit down with him so I can make sure that I'm not, you know. Okay. So, so basically, everything on the board is how you calculate an opacity, if you will, optical depth opacity, for a line. Okay. This next chapter was how do you calculate the continuum opacities, and all the formula are there as well if you really want to learn how to do it. So if you want to print those notes out someday and learn about continuum opacities, they're all there, or maybe you'll learn about it in Jason's class. Heck, maybe my notes might even be helpful in Jason's class. Maybe. Maybe not. Okay. Okay. What I hope to have done here at the end of this class is have you appreciate what causes a spectral line to happen, and then how you actually model your data to learn about the physics of the material through which that generated that light or absorbed that light. You know, like anything else, you have to practice it and do it to really, really learn it. But I think I've painted the picture for you at the very least, and then you've had some exercise in modeling the gas. Not modeling the profiles, however. Now, if you haven't done your evaluations already, I am very open to, you know, comments of the nature of, hey, I really wish we'd seen this. We didn't get to it. I would have liked to see more of it. Hey, we did too much of that. So that, you know, for the future I can improve the class. And any comments about that, regardless to homeworks as well, that would be good. Okay? All right. And also comments about recording it was good. don't do it on the screen, that stunk, or I liked it on the screen better. Whatever you want to say, it'll be helpful. Okay? Yeah. All right. Okay. Hope you had a good semester.